So anyway, one reason that we did the integral of the secant last week was that we'll be led to that particular integral in problems of this type when you have made the substitution to replace the original sum of squares. And now, this is not yet the answer, because this is the answer in terms of the new variable t, and if it's an indefinite integral, you have to get back to the original variable. If it were a definite integral, then you could change your limits on x to new limits on t, and then you could work from here with the new limits. But as it is, what you do is you draw a right triangle in the first quadrant, and your relationship here, if you solve for tangent, is it equals x over 3. Well, in your right triangle, if you put your angle down here in the corner, your tangent is side opposite over side adjacent, right? Right triangle trig. So then that means if x is here and 3 is here, your tangent of t is x over 3. Then you use the law of Pythagoras to get the third side, and you notice that the third side of your triangle is exactly the two-term expression that you did all this trickery to deal with. That's always the case in these problems. When you're going back to the original variable, you use a right triangle drawing, and what comes from your substitution is a trig function equal a quotient, because they are ratios of two sides of a right triangle. And so you identify your two sides from the numerator and denominator in the quotient that you're defining with your trig function, opposite over adjacent or opposite over hypotenuse if it's a sine, and so on. Law of Pythagoras gets the third side, which will be, or which will involve anyway, exactly the sum or difference of squares that you started with. So that's kind of a check. So then from here, you can say cosine is the 3 over the square root, and then secant is 1 over the cosine, so turn the cosine upside down. That's how I do it. I can remember the ratios for sine and cosine and tangent, and then I turn them upside down if I have a cotangent or a secant or a cosecant. Okay. So then your answer for problem 1, you see, what you have now is you have secant in terms of the original variables, and you have tangent back here. So your answer, which is log secant plus tangent, is log secant, which is your square root over 3, plus tangent. And when you do the integration for secant, you always put absolute value here, log of absolute value, because log is not defined unless what you're taking the log of is positive. But when you look at what you have here, you have a square root of the sum of squares. There's no way that's going to be negative, and your x is not negative because you're assuming that you're working in the first quadrant to begin with. So you really don't need the absolute value there. It doesn't hurt if you want to write it, but you don't need it. Notice there's a little more trickery here yet. I wrote this plus a constant with a subscript, C1. Now, you notice you have a common denominator on these fractions. And so you could have written this square root 9 plus x squared plus x, all divided by 3, just as well. Okay, the log of a quotient is the difference of the logs. So you could have rewritten this as log of the sum of the two numerator terms minus log 3 plus constant C1, and then constant C1 minus log 3 is just another constant you could call C2. And so you could write your answer log of the square root plus the x plus some constant. And that's what you find in the back of the book. So you can play tricky games with constants on these indefinite integrals. A question here on problem 1. There's trickery here certainly, but you notice that with tricks of this sort you can do the kind of looking integrals that we have in this section that involve sums or differences of squares. And often that sum or difference is under a square root or something like that. Here's a definite integral, and you notice you have a difference of squares, the constant minus the variable type. And so that's your sine cosine type substitution. So based on what I said back, I would take x as 3 sine, then your dx is going to be 3 cosine, and then your 9 minus 9 sine square is going to be in here as a 9 cosine square, and then when you square root 9 cosine square, you're going to get 3 cosine. So this is going to become 3 cosine without the square root, and you're going to have 3 cosine up here from the dx. So the integral then is going to be 3 cosine t to the dx, square root of 9 cosine square, which is 3 cosine t at the bottom, dt, and since it's a definite integral, the thing to do is get the appropriate new limits. So we have x equals 0, and we have x over 3 equals sine t. So sine t is going to be the 0 over 3. So sine then is 0, so the t is 0. So the new bottom limit on t is also 0. But for your top limit, your x is 3 halves, and your sine t is x over 3, so it's 3 halves over 3, so sine t is a half. Okay, so if sine t is a half, t is arc sine, 1/2, which is your 30 degrees. But you don't say degrees. In calculus, it's always radians. Why is it always radians in calculus? Answer: because the derivative of the sine is not the cosine unless you're in radians. If you're in degrees, the derivative is pi over 180 times the cosine. And so radians were cooked up so we don't have to say pi over 180 every time we open our mouths with a calculus formula. So it's always radians. And so it has to be pi over 6. And as we've already said, these are identical. So you have the integral 0 to pi over 6 dt, which is t, 0 to pi over 6. So your answer is pi over 6. And you see the degrees or radians issue is important because the answer is pi over 6. The answer is not 30 degrees. Again, if you look at the sides of the right triangle, where sine t is x over 3, here's your x, your hypotenuse. Law of Pythagoras gets you the third side, and that's exactly what you were playing all of this game to avoid, is dealing with this square root of the difference, 9 minus x squared. That's always going to be true with these substitutions and using the right triangle to get from one variable to the other. The third side of your right triangle, OB, will involve anyway the sum or difference of squares that forced you into all this. Now take a look at 7. You have the square root of 25 minus t squared. Now, if you think back a couple of weeks, you should recognize that we have this integral. So what I have here is a review for a minute. When we were in 6.5, it was the kind of thing where we, if you remember the 6.5 problems, a lot of them were work done by variable force like Hooke's law and whatnot, or lifting the bucket where the water was leaking out in the sand or whatever. And then we had in that same section, we were pumping water, somewhat like the problem on the test, where we were pumping the liquid chocolate. And then we had the ones where we had force due to the weight of the water, or could have been any other fluid, on one side of the wall of the container. And problem 36 was one of these, where the water is 6 feet deep, and you have this half circle window, if you want to think of it as if it's a big tank and people are looking at the sharks or whatever is in there. And so the top here was a foot down. This had a radius of 5 feet, and so the high point here is a foot down from the free surface. And we were calculating this force. So we had a strip across here where the window part is. If you take your origin here so that y is the height to this representative slice, then it's 6 feet up from the origin to the free surface of the water, and 6 minus y then is the depth. You remember that your Pascal law is that the pressure is the depth times the density of whatever the stuff is, the water, say. And then your force is, well, first of all, it's pressure per, pressure is force per unit area, so force is pressure times area. So it's density times depth times area of the representative slice. So this strip has a length of 2x if your y-axis is here and it's x each way, right or left. And we have the formula for the circle when the origin is here, which would be the sum of the squares equal the squared radius. So then your x, if you solve this for x, is square root 25 minus y squared. That's there to there, and it's the same going to the left. So your length of your slice is 2 square root, and that times dy is the area, and then density times depth times that area is your force against this. So we had this a couple weeks ago when we were doing that problem. Well, if you remember back when we were doing that, our force would be the integral here, and you see there are two integrals because there's the density times the 6 times the 2 times the square root, and there's the density times the minus y times the 2 times the square root. So that gives you these two integrals to do. And this one we could do, this was a u substitution. If u is 25 minus y squared, the du is the minus 2y dy. And if you can remember back, we had this one, and I said at the time, this is something that we don't know how to do. And I referred you to the formula in the back of the book, number 45, in the appendix. And we did this one in class by referring to that formula and substituting into the formula. Okay, so this is basically that same integral. See? Whether it's 25 minus t squared dt or 25 minus y squared dy, it's the same issue. So now we will see how you do it. In other words, how they got the formula that's in the back of the book. If you can remember the formula in the back of the book, it involves an arc sine. So with this morning, so far, that ought to make a connection. We do these trig substitutions. We do, if it's a square minus u square, substitute in a sign, and so that's where that arc sine might be coming from. Okay, so back to here now. We let t be 5 sine x, square root of 25. dt is 5 cosine x dx. So then this will become 25 times 1 minus sine square. And of course, that's 25 cosine square under the square root. And of course, that's your 5 cosine. Then you also have dt is 5 cosine x dx. So your square root here is 5 cosine x. Your dt is 5 cosine x dx. So altogether, you have 25 cosine square dx to do. So then what you want to do is think about your recipe from the trig class. So we go over here to the recipe box where 2 cosine square is 1 plus cosine 2x, and 2 sine square, for good measure, is 1 minus cosine 2x. You use those so much in doing integrals by hand that it's worth trying either to learn them or to learn where to find them, let's say. And so using that, you see, I'm replacing my cosine square by the 1 plus cosine 2x. See, it would be over 2, and then the 2 I put out in front. So there's the 2 that would be this 2. And so when I integrate the 1, I get x, and that's where that arc sine is going to come from. And then when I integrate cosine, I have sine, and if it's cosine of a times x, it's sine of a times x over a. So now we make the same substitution triangle that we've done in the others. So our substitution was sine x was t over 5. So there's t, and there's 5, and there's x. And this over that is sine. And then your third side, sure enough, that's the square root that you're dealing all this trickery to try and get away from. And so your cosine is the square root over 5. So the reason that I need cosine as well as sine here is that I have sine 2x. So I have to use a trig identity that sine 2x is 2 sine x cosine x. You had problems of this sort in either Math 144 or Math 147, where they give you the triangle and then they want you to tell them what sine of 2x. You see. So what you have to do is take the triangle and get sine x and cosine x as you read it from the triangle, and then use the trig identity for sine 2x, that it's 2 sine cosine. I'm sure you remember suffering with a lot of those things like that. So then the sine 2x over 2, which is 2 sine cosine, notice those 2's cancel, and then you have sine x, which is t over 5, and cosine x, which is the square root over 5. And then from this first part, where you have the integral of dx giving you x, the x is your arc sine of t over 5. And so that's going from the x that's here, when you do this integration, to arc sine t over 5. That's why there's the arc sine in that formula in the back of the book, number 45. So then finally, you could go on from there. This was an indefinite integral, so you would just be leaving it with the arc sine and like this in terms of the original variable. In the formula 45, instead of 25 minus the squared variable, it's a square minus the squared variable. So then what you would have, if you actually look at the formula in table T2, instead of this you have a square over 2 and arc sine of, I think the variable actually is x over a, and then you notice this times this is the a square, and so then for this part you have your variable over the 2 and then the square root. So the formula is equivalent to this, although it's written just a little differently. So that's where it comes from anyway. It's this section of the book. Meanwhile, take a look at number 10. So this is variable square minus constant square. See, so this is a different case from the others. And the reason that it says x is greater than 3/5 is so that you're not trying to take the square root of a negative and by greater then this is in fact positive here, so you're not dividing by 0. See, if x were equal to 3/5, your denominator would be 0, and you're not allowed to divide by 0. And if x were less than 3/5, you'd have a square root of a negative, and you can't do that. So that's why that's in there. So let x be whatever would be your square root of this number over that one, which in this case is 3/5 secant. And then your dx is 3/5 secant tangent. And then you see if you have done that, your 25x minus 9 is 25. The x is the 3/5 secant, so the x square is 9/25 secant square minus 9. You notice the 25's cancel, the 9 factors, and your secant square minus 1 then will be your tangent square. So your square root becomes this square root, which becomes this one, which becomes 3 tangent. And we're thinking of this in the first quadrant. So the original problem then, I factored the 5 out, and my dx was 3/5 secant tangent and dt, and then my denominator was 3 tangent. And so the tangents cancel and the 3's cancel. And this 5 cancels that one. So I end up just integral of secant. And we talked about how you do the integral of secant. Log secant plus tangent here. And so what you have to do now is replace secant and tangent to get back to the x. Well, if x is 3/5 secant, then your secant is 5x over 3. Okay, and then your cosine is 1 over secant, it's 3 over 5x. So I go back to sine or cosine to draw my picture, because that's the limit of my mental capacity. So I'm honest. And so if I'm back to cosine, I know, oh, that's side adjacent over hypotenuse. So I make my numerator the side adjacent, and my denominator is the hypotenuse. And then I do the law of Pythagoras for the third side, and sure enough, that third side is this same square root that we were working, that we were doing all of this substitution game to try and get away from. It always comes back to you as the third side of this substitution triangle. And so there it is. Okay, so then when you want to form secant and tangent, this third side will appear somewhere. Okay, so your cosine is 3 over 5x, so your secant, which you're replacing here, is the 5x over 3. And then your tangent is opposite over adjacent, and so this appears as the numerator in your opposite over adjacent quotient. So finally, you could write this. Now you can play the same game again with logs. So you have a common denominator. So you have log 5x plus the square root minus log 3. And then a new constant is the original one minus log 3. So you could say it like that. in the book, they wouldn't bother with the subscripts. So the book will just have log of 5x plus the square root plus constant. And one thing it will have is its log of the 5x plus the square root is the argument of the log, so make that.
Another bracket.
I had one there, but it wasn't very clearly printed, I think. I think you can see now that the 5x plus the square root is the argument of the log. That's what I'm trying to say, anyway. Okay, any question on this? Yes?